So basically, experiment 1 had to do with the determination of ionization constant of acetic acid. Acetic acid we know is ethanoic acid, right, which is CH3COH. So what happens when it dissociates in solution, right? So this is an equilibrium symbol. So the ions get to pathways, all right, and you have that, all right. Sorry, yeah, you can see that in your manual. So this is what it gives you in solution, these ions, right? So now Ka is the ionization constant, and we want to determine the extent of ionization of acetic acid. So that means we want to know how strong or how weak that acid is. So ionization constant is denoted by Ka, all right? That is that. Now, there is a relationship that connects pH and the strength of an acid, and that is why we employ the method of pH to actually determine the extent, to know the extent, the strength of that acid, all right? So there's a relationship that exists between pH of a solution and its strength. The pH has a relationship on the strength of an acid. So that relationship is also in your manual. If you go through it, you get to see it, and that is the main thing you're supposed to know. You're supposed to know that relationship, even though I'm not the one taking the course, because that is a major emphasis, okay? And this is the relationship where you have the acid or base, right? This relationship is there, okay? So essentially, you'll be expected to plot a graph after deriving the pH of the solution. You plot a graph of pH, let me write this correctly, pH against the log of the acid conjugate base, sodium ethanoate, right? That is the conjugate base. It has some basic characteristic. What I'm trying to say is the base here, let me write that log, all right? We have CH3 COONA, all right? Then we have CH3, which is the acid, all right? This is what I'm trying to say. After taking the ratio, the volumes from your table, you can see it. After deriving this, you are taking the variables, that is this one, plotting a graph of pH against log 10 of the acid base ratio, all right? And these values, the values here, right, and their pHs would correspond. So you plot a graph of pH against this. That is essentially the task in this experiment. So you have to plot a graph of pH against that. Then you determine the Ka of the acid from the graph. How would you determine that? Definitely, this is the kind of question you will get to see, definitely, all right? So the Ka is derived from the slope of the graph, all right? So whatever you get as your slope, once you've plotted the graph, just a minute, once you've plotted the graph, okay, you plot a graph of pH against the log 10, right, of the acid and base, right? So once you've plotted the graph, I'm not going to tell you what sort of graph you're going to get. So it depends on the graph you get based on your own correct deduction observation. So, but the slope you derive from this graph is going to be your pKa. And we know what pKa is. pKa is the negative log to base 10 of the Ka, which is the dissociation constant. So it's the negative log. So that's just literally what it means. So it gives you an insight on the ionization constant, which is the Ka, because as Ka increases, pKa decreases. Do you understand? So whatever value you get, you're supposed to compare with standards to be sure that that value is that of acetic acid. All right. So in this experiment, be sure to know how to plot. Be sure to know how to plot. That is one. Be sure to know how to determine the Ka of the acid. All right. Know the relationship that exists between the Ka, the pH, and the pKa. All right. So, and be able to make deductions on the value you've gotten. All right. So, and that is basically it. Just know how to plot the graph and how to interpret it. All right. So this is how you get you go about determining the dissociation constant of acetic acid. All right. So that's just basically it for experiment 1. The relationship is very much important. No one is going to ask you to start proving to derive how the expression pH equals to pKa blah 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 minus log 10 of the acid base. No one is going to ask you to do that. So just focus on what the experiment as a whole was all about, how it was done, all right, and how to make up for your tables. Know how to account for the individual variables in your tables. I'm talking about the values. How did you get them? And also know how to plot your graph. Choose your scale correctly. Good scaling is important. All right. Choose your scale correctly. All right. And know how to interpret and know how to calculate your slope. You know how to calculate your slope, right? So you do all that, and then you get your pKa, which will give you an insight on the Ka. Then use the relationship that is between them to derive your final conclusion. Like I said, no one is going to ask you to prove. All right. No one is going to ask you to prove. So don't forget that pKa is equal to the negative log 2 base 10 of the Ka. So this is just a relationship. All right. So, and that is why you're actually plotting a graph of pH against the log of the acid base. That's the dissociation constant. Right. So also know this expression just in case, and it's from here you make informed decision on how to write the formula, all right, for showing the dissociation constant. Okay, but nobody's going to ask you to prove it. So that's basically experiment 1, determination of ionization constant of acetic acid by means of using pH. All right, pH of the solution. All right, that is that about this experiment. For the second experiment, you will be exposed to the use of the UV visible spectrophotometer, right? Okay, so that is basically what experiment 2 will dwell on. So, and the principle behind this instrumental technique is very important. It's very important you get to know the principle guiding it. All right. So this technique applies what we call the Beer-Lambert's law, or the Beer's law, okay, which actually states that the absorbance of light, the absorbance of light by a solution, usually colored solutions actually, is proportional to the concentration. Absorbance of light by a solution is directly proportional to the concentration, all right, of the absorbing species. Those things that are responsible for the absorption are the concentration, all right. So the absorbance of a solution, right, is directly proportional to the absorbing species, those things responsible for the absorption, those analyte. The analyte is the chemical species of interest. They are the ones that would absorb this light in the UV region of the electromagnetic spectrum. All right, and you already know the range, around 400 to so nanometers, right? So that is basically what Beer came up with. All right, that the absorbance is directly proportional to concentration of the components or the analytes or the species of interest in the solution that are usually colored. All right, and it is not just only applicable to the concentration of the components of the solution, it is also directly proportional to what we term as the path length. The path length L. All right. So in a nutshell, A is equals to E CL. Can you see? The path length is the distance traveled by the light, that's UV light, through the sample. If we have a sample like this, and this is incident light, all right, this is emerging light, right? So the distance the light will travel within the sample is called the path length. So you see, the absorbance of this solution in this cuvette, because the cuvette is where you introduce the sample, right, before you place it in the spectrophotometer. So the absorbance of the component of the solution within the cuvette is directly proportional to the concentration. So the more the absorbing species, the more the absorbance. And it is also proportional to the distance the light, incident light, is able to travel within the sample. So that is basically it. You should know the relationship very well. All right. A is absorbance. This is molar absorptivity. Molar absorptivity is E epsilon. You can see it here. This is molar absorptivity. All right. So it is a measure of how, to an extent, a substance gets to absorb light at a given wavelength. So it's a degree of absorption. Tells you the degree to how strong that substance, all right, absorbs the incident light. So this is just like a degree. All right. And something you should not forget is the units. All right. Don't forget to know the units for each and every parameter. So path length is just distance. So go through this, know the units, and know how to apply them correctly. Concentration is in mole per liter. Like I said, path length, centimeter. All right. Molar absorptivity, when you, let me show you guys something here. When you make epsilon the subject formula, you are going to have this, right? So this quantity will inform you on the units of molar absorptivity. I need you guys to do that by yourselves, because it will help you in a case a table is given and you're expected to plot a graph. And you know that while plotting the graph, usually you plot a graph of absorption against concentration, because you want to know the concentration of the absorbing species. Don't forget, this concentration has to do with the concentration of the absorbing species. At what wavelength do they absorb maximum? Don't forget, maximum wavelength is what we are always looking at. And that is why you were expected to prepare different solutions of, that is K2CrO4, that is potassium tetraoxochromates, all right, 4 times 2, 8 minus 2, 6. So potassium tetraoxochromate 6. All right, and that is that. And why are you, I usually tell you guys to know the function of reagents. In any experiment you are carrying out, try to know what is the role to be played by that reagent. For example, this species here, potassium tetraoxochromate 6, is going to serve as what we know as the primary absorbing species. All right, so it's going to serve as our primary absorbing species that will help us to study how the absorption of light is varying with the concentration and the wavelength. So usually you carry out the absorption at different wavelengths. In your procedure, you get to see that, and your aim is to have a range of absorbance values that would help you to derive a calibration curve. All right, so first off, you're going to have this graph. You're going to have an absorbance wavelength. This graph will give you the maximum wavelength of absorption, and this maximum wavelength is called lambda max, maximum wavelength. All right, so with this wavelengths, right, different wavelengths, you have to vary them. Okay, you now get the peak wavelength, telling you this is the wavelength that the absorbing species, that's the component of the solution, is able to take in, and it will give you idea on the concentration of the sample absorbing at this wavelength. So once you're able to know the maximum wavelength, what happens usually is that the UV spectrophotometer is now set or configured to that maximum wavelength. All right, it is now set at the maximum wavelength, and then to now know the concentration of your sample, the analyte of interest in your solution, you then have to run the different concentrations you've prepared. I guess you guys prepared different concentrations, right? Like that, different concentrations of the solution. And meanwhile, let me not forget, in your manual, you also employ the use of sodium hydroxide. Like I said, you need to know why these things are used. All right, so you made use of this for the preparation. All right, various concentration of the potassium tetrahydrochromate 6 KCr04. Right, you used sodium hydroxide in the preparation of the various concentration of the potassium tetrahydrochromate 6 solution. All right, and this is so because you needed to correct any solvent absorption such that every absorption is dependent on this one. All right, it's used for correcting the solvent absorption. All right, so it's more like serving as a blank reference for correcting solvent absorption. So in order to initiate, to start up the experiment, you have to prepare a series of dilute solutions. So like I said, once you've derived your maximum wavelength, you now have your solutions prepared. All right, then each of those solutions, you now want to know their different absorbances. Remember, you've prepared a series of solutions like that. Then you now want to know their different absorbances. Solution 1, all right, or their concentrations, all right, different concentrations, right? Now you now want to know their absorbances. A, this is concentration. You take the first one, put it in the spectrophotometer that has been set at the maximum wavelength. Remember I said this, all right? The spectrophotometer will be set at the maximum wavelength of absorption in the first stage of the procedure. That is the aim, to know the maximum wavelength, all right? So don't forget that. So the solutions you prepared, you now subject them again to find their individual absorbances. So they'll give you different absorbing values. So this one, the same thing, right? So in the long run, you have a graph that looks like this, okay? Concentration of the prepared solution, you've known their absorbances, all right? Then remember, the initial procedure gave you an idea of the maximum wavelength, which is lambda max. Then what you're expected to do is, at this lambda max, this lambda max corresponds to a specific absorbance, all right? This lambda max, don't know if this is visible enough. That's the previous graph illustration I showed you guys. This lambda max, all right? Remember, wavelength, varied wavelength was what happened in the initial stage. Then you got series of absorbances. So this maximum wavelength, the highest wavelength of absorption corresponded to an absorbance, all right? Now it is that absorbance you would now, in the second procedure, find here. Let me show you. It is that absorbance you will now find here. If the absorbance was, let's say, 5 or thereabout, then you locate 5 based on the lambda max, right? In the initial procedure, you locate it. Then once you've located it, you now extrapolate. Extrapolate, just draw a line like that until the line touches this line, the straight line. Then you now extrapolate downwards to this concentration axis. This is the x-axis. So whatever value you get here is the concentration of the absorbing species. So this is how you get to determine the concentration of absorbing species using UV visible spectrophotometer. So you have your working wavelength, lambda max, you know the maximum wavelength and the absorbance, the maximum absorbance at that wavelength. So that is what you will find. Once you plotted the graph, you will locate it, extrapolate, then you find the concentration of the absorbing species. So this is called your calibration curve. All right, it's called the calibration curve, or you can call it the concentration curve, whichever suits you the best. So now if you look at, if you think, I saw somewhere in your manual that tells you how you're going to plot the graph, which I've already explained just now. Okay, so what you have there is you are asked to plot a graph of absorbance against wavelengths. Absorbance against wavelengths of the potassium chromate solution. That was the first thing that will give you an idea of lambda max, which I said, once you plotted the graph of absorbance against the series of varied wavelength intervals, right? So it will give you the absorbance. This is one thing you need to know because we are working with the maximum wavelength of absorption. Then secondly, you now plot a graph of absorbance against concentration of the mixture you've prepared. Each of those mixtures, you subject them, you get values. So now your scaling is very important. You need to know your scale, and your scale will be based on this lambda max. If, for example, is 10, so that means your absorbance range here should cover up to 10. Do you get it? It should cover up to 10. So each of those concentrations, you know the concentration you've prepared, you write them like that. however you prepared it, you indicate it here on the y-axis. So they will give you, just like I've explained, then you get your straight line graph, right? So remember, the slope is your molar absorptivity, all right? Path length usually varies, but then you should also know the path length. So that's basically that. Then you calculate the molar absorptivity at each concentration. So that means you're going to have a graph, a table that show the different concentration. So the table should have concentration, you should have the absorbance, you should have the wavelengths, right? You should have the molar absorptivity, since you are asked to find the different molar absorptivities, right? So you should have this. Okay, you already know the path length, usually variable anyways, but you have to know the path length. You will now calculate the various parameters that has been requested of you. All right, then you now determine the extent of deviation from the mean and give reasons. All right, there's always a reason, so you get to find the deviation, standard deviation. What is that formula? Summation of x minus x bar over n. Yeah, I guess, yeah, if I'm not mistaken. This is the deviation, so you have to find for each of the components. This is the mean and this is the number of observation. The number of observation from experiment, I guess, is 9. So you find for each of the components, right? Then you have the mean. So you do that to find the deviation. You know, mean is x1. Mean is x1 plus x2. That's over. Yeah, over n. So x is each of these x1, right? So you do that. So you get to calculate the extent of deviation from the mean, and then under what conditions is Beer-Lambert's law not obeyed? All right, that you can actually deduce by yourself. So in a nutshell, this experiment, yeah, you should know the theoretical aspect of this experiment so much, all right, and how to plot the graph, just like I've explained in the previous experiment 1 on dissociation constants. Okay, so that is just an overview of that experiment. So for the other experiment, I can actually say I don't know how many of the experiment that you all were able to conduct, okay, because basically I just wanted to provide an overview of the major experiments that you covered. But I know definitely experiment 1, experiment 2 must have been covered, and that is why I'm providing the just an explanatory presentation on them. Okay, so with the knowledge you've derived from 1 and 2, follow same way to study the other experiments that you might have conducted. All right, and be sure to know why each of whatever component, whatever subject of interest is being taken into account. All right, so good luck. And basically it, yeah, experiment 1 and 2, I believe they are the very much significant experiments in this course, definitely. And I know you might not expect, I don't think you would I don't think anything other than 1 and 2, or let's say 3 questions or 4 questions might come up. 3 to 4 might come up. I'm just trying to speculate, but then I know definitely 1 or 2 must be part. So since they are the introductory aspect of the course, so be sure to study in the same way I've explained 1 and 2 for your other experiment, because I don't know which of them you guys carried out. So that's why I have to stop it here, and you have over 5, 6, 7, I don't know. All right, so good luck, and that is it.